We're going to start talking about projectile motion. What did I tell you projectile motion is? It's an arc, right? It's moving through the air in two dimensions. So objects that are moving both horizontally and vertically. Up until now, we've really only worked with objects that go straight up and down, or they go straight side to side, right? And so now we're combining both of those things. A lot of examples in everyday life of projectile motion. Anytime we throw or kick something, anytime we launch something, we jump, right? If we jump forward, like in long jump, those are all examples of projectile motion. There's a lot of different things we can think of as examples of projectile motion. Okay? When we talk about projectile motion, we are not at all concerned about how the object got set into motion. All we're concerned about is once it becomes a freely falling, freely moving object, that's what we're concerned with. We're not concerned with the kick that put it into motion or the throw. We're concerned about what's happening the second it becomes moving like by itself. Okay? Yeah, sorry. All right. Galileo was the one that first kind of accurately described and walked us through projectile motion. He understood and he really laid out that we have to analyze vertical and horizontal motion separately. That might be something that you should highlight, I think. We have to analyze horizontal and vertical components separately. So that's why we spent time in this last section breaking down our vectors into horizontal and vertical components. Because if we're given an initial velocity that's at 30 degrees north of east, we can't plug that into a kinematics equation. We have to separate it into kinematics in the x direction and kinematics in the y direction. Okay, so that's kind of be our goal here in the next couple lessons, okay? So there's a couple of things that we have to assume for projectile motion, right? In high school physics, we live and we participate in like the ideal physics world, right? Where we ignore air resistance and we ignore all these different things. And so in this perfect physics world that we live in, we're gonna assume that we can ignore air resistance, right? Air resistance is gonna be negligent for us. We're always going to assume that our time is starting at zero, right? We don't care what happened before. We just care about the start of our motion. That's the same that we've done with kinematics up to this point. We've always assumed that our time started at zero. All right, we're always going to assume that motion begins at the origin, that our xi and yi are zero. That's the same as what we've been doing so far also, right? That's not new. We always said that y initial and x initial are zero. But those are some things that I wanted to remind us about, okay? The first thing we're going to start with today is something called a rolling projectile. And I don't know if that's the real name for it, but that's what I call it. Okay, a rolling projectile. And I want you to think about an object that rolls off a table, okay? It rolls off a table. Now, when we would look at this, let's just draw a little image here, okay? So I've got an object. Here's my table. Here's my ball. It's rolling. Then when it gets to the end of the table, does it just go like that? What's it going to do? It's going to go forward and down at the same time, right? It's going to move in both of those directions. Okay, if I was going to examine this motion, the origin gets set right here at the end of my table because I don't care about necessarily what's happening with the ball right here. I care about it when it becomes a freely falling object. So what happens before is going to have some effect on our numbers, but we don't care about the fact that it's moving right here. We don't really care about how it got started, okay? But I would set the origin there at the end of my table. We're going to treat our horizontal and vertical components separately. So if I look at this image again of the ball rolling off the table, our vertical components for V, Y, I is zero. So let's walk through this. What would VYI stand for? VYI. What would that stand for? Velocity initial in what direction? The vertical or the Y direction. So this would be initial vertical velocity, right? Do you see it? We've got two different subscripts there, but they all tell us something. Velocity initial in the Y direction. Okay, and it says that my object has a VYI of 0. Okay, so right here, the ball leaves the table, but which way has it been traveling right now? Has it been traveling vertically or horizontally on the table? horizontally. So that means the second it leaves the table, it's still traveling horizontally for just a second, and then gravity starts pulling it downward. Okay, so in a rolling projectile, our VYI is always going to be 0. Okay, in a rolling projectile, in something that leaves a cliff or a table or whatever horizontally, it's going to be 0. Okay, you need to kind of, we'll use some context clues to help us figure out that that's the case. But VYI is 0. My acceleration in the y direction is always negative 9.8, just like it was in our previous problems. Okay, in the x direction, there's a couple things that we need to think about. In the x direction, I want you to think about purely horizontally. Purely horizontal. If we can ignore friction, if we can live in a perfect physics world, do things speed up or slow down in the horizontal direction without something else acting on it? No, right? Newton's first law says an object in motion will stay in motion unless it's acted upon by an outside force. So if we're ignoring the force of friction, if we're ignoring all of that stuff, right, we're living in our perfect physics world, an object moving in the horizontal direction will not randomly speed up or slow down, right? It will just keep rolling. And so that means the acceleration in the x direction is always going to be 0. Acceleration in the x direction is always equal to 0. Okay? When things move in the vertical direction, they slow down, right, as they get to their highest point, and then they speed up on their way back down. But that does not happen horizontally, right? Things just move at a constant speed horizontally. So no horizontal acceleration. Okay? If that's the case, if we have no change in velocity in our horizontal motion, that means that Vxi must be the same as Vxf. Okay, do I need to say that again? If we have no acceleration, if there's no velocity change, that means that my initial horizontal velocity must equal my final horizontal velocity. Okay, so we're going to walk you through the equations for projectiles here in just a second, but I want to give an example here. Okay, which will hit the ground first? A ball that's rolled off the table or a ball that's dropped from the same height? Okay, how many of you think the dropped one's going to hit the ground first? How many of you think the rolled one's going to hit the ground first? Okay. They're going to hit the ground at the same time. Same time. Got any guesses why? What'd you say? Gravity's acting on the same. That's right. Gravity's acting on the same. They are falling from the same height. The x component has nothing to do with the y motion, right? Nothing to do at all with the y motion. So here's what it looks like frame by frame, right? The yellow ball is moving both horizontally and vertically. The pink ball's just moving vertically, but they are going to hit the ground at the same time because the x component and this y ball has nothing to do with the vertical component, right? It is moving forward, but it is falling at the same rate as the pink ball. Equations should go on your equation sheet in a separate category. It's called projectiles. Okay, so on your equation sheet, give yourself some room for projectile equations. They are very similar to your kinematics equations, but they're a little bit different, and I'll walk you through why they're a little bit different here in a second. So get these ones copied onto your equation sheet under the category or the heading of projectiles. Okay, and then label them as vertical and horizontal. Okay, so kind of give them some separation there on your equation sheet as well. Okay, what did we say? I want to show you how these horizontal equations came about, okay? If I take my regular kinematics equations, Vx final equals Vx initial plus Ax times t, what did we say Ax is always equal to? What's acceleration in the horizontal direction? It's always, horizontal. It's always 0. So that means that part of the equation just drops out. So here's where that first equation came from. The second equation comes from the second one. X final equals X initial plus Vxi times t plus 1/2 Axt squared. But what do we say Ax is equal to? 0. So that whole term drops out. So that's where that third equation the second equation comes from. If I take the third one, Vxf squared equals Vxi squared plus 2Ax times delta x. What do we say Ax is equal to? 0. So then I have Vxf squared equals VXI squared. And isn't that the exact same thing as that? Yep. Okay, so that's why those horizontal equations get to be pared down a lot, is because AX is equal to 0. So let's try one. This says a stunt driver speeds horizontally off a 50-meter high cliff. This horizontally right here, it speeds horizontally off a cliff. That's the big clue for us that it is a rolling projectile, that we're going to solve it in this way. Okay, how fast must the motorcycle leave the cliff if it's to land 90 meters from the base of the cliff? So I'm going to draw up on top a little motion diagram. I'm going to encourage you to kind of do the same. Okay, my cliff is 50 meters tall. Here goes my motorcycle. He needs to land this distance to be 90 meters. Start identifying and matching these numbers with some variables, okay? The first thing that we've got to know is our cliff is 50 meters high. So what variable could that fit with? Here's my origin. So my y final is going to be negative 50 meters because it's landing 50 meters below where it started. Are we on the same page with that? Okay. Then what is my other displacement given? 90 meters. What's that going to be equal to? XF. Good. And it's going to be positive 90 because it's forward, right? It's moving forward. Do we see how those two variables get put in with different, those two numbers are different variables, right? One is the vertical displacement. One is the horizontal displacement. Okay. The fact that it says it's speeding horizontally off of a cliff, what does that tell me about its initial velocity right here? Is my initial velocity vertical, horizontal, or both? Only horizontal. So that's actually what I'm solving for, right? How fast must he leave the cliff? I'm trying to find VXI. That's my question mark. But since it says it speeds horizontally off the cliff, that automatically tells me that VYI is 0, right? In rolling projectiles, we said VYI is always 0. So this context clue here, it speeds horizontally off a cliff, is really important for us, okay? This right here, if it says it dives horizontally, it rolls horizontally, it speeds horizontally, whatever you do, if you have that clue there, we know it's a rolling projectile, and that tells us that VYI is equal to 0. Okay, so that context clue is really important. Okay? So now if I know I'm trying to solve for VXI, I need to look at my equation sheet and say, what equations do I have that can even get me to VXI? Okay, so grab your equation sheet out in your calculator if you don't have those out. What equation do I even have that could help me solve for VXI? Look at your horizontal equations. Yeah, the first one doesn't tell me anything, right? I can't solve anything with the first equation. It's just telling me that my initial and my final are equal. The second one, it says XF is equal to XI plus VXI times time. Well, I know that XF is 90. XI is always what? 0. So if you want to put that in your list, you can. You don't have to, but you can. I'm solving for that. That's my question mark. But do I know time? No. So I want you to look at your equations. What's the one variable that is in both sets of the equations of vertical and horizontal? There's only one variable that is in both. It's time, right? Time is the only thing that's not affected X or Y, right? It applies both X and Y. It's the same amount of time. So time is the only variable that can cross over between the sets of equations. So now I need to go pick out a vertical equation to use to solve for time. Then I can come back to my horizontal set. So take a look at your vertical equations and see which one do we have that can help me solve for time. I agree. I think the second one as well. Okay, so let's go look at this second equation. Y final, is that green? Hard to see, sorry. Y final equals Y initial plus VYI T plus 1/2 A T squared, okay? Y final we said is negative 50. What's Y initial always? Initial displacement is always 0. What do we know in this equation about VYI? It's 0 as well. 1/2. Acceleration in the vertical direction is negative 9.8. And I'm solving for t. Okay, I need to know what questions we have about setting up that equation. Okay, then we just solve. .19 seconds is going to be the time it takes for an object from this height that is dropped or starting at 0 to hit the ground. So we know by the time our object hits the ground, it's also going to travel 90 meters. And so this time applies, right? So now we can plug our time back into our equation up here. X final is 90. X initial is always 0. VXI is what we're solving for. And our time is 3.19. And so we're going to divide that over and we get a VXI equal to 28.2 meters per second. A rock's thrown horizontally from the top of a cliff that's 24 meters high with a horizontal velocity of 3.21 meters per second. How long is the rock in the air? So we've got a couple, actually it's got one more question. Oh, it wants us to answer a lot of different questions. Okay. It asks us, how long is the rock in the air? How far from the base does it land? And what's the final vertical velocity of the rock? So we're going to look at 3 different things here, but our motion diagram pretty much looks the same, right? We've got some cliff. Our object's going to go off the edge and then it's going to fall. It says our cliff is 24 meters high. Okay, so this clue right here, thrown horizontally, tells me what about VYI? Right, it tells me that the second it leaves my cliff or my edge, it's moving purely horizontally. So VYI has to be equal to 0. Right, that clue right there tells us that VYI is equal to 0. Because it says all my velocity at the beginning of my motion is horizontal. It is purely horizontal. And it happened to give me that. VXI is equal to 3.21. Okay, what does this 24 meters give us? My displacement, good. And is it vertical or horizontal? Vertical. So YF, is it going to be positive 24 or negative 24? Negative 24 meters. Okay. It asks me for how long is the rock in the air. So time is going to be my question mark. And we'll go ahead and solve that first, and then we'll kind of go from there to answer the rest of our questions. So do I have an equation here to help me solve for time? You can look at your vertical and your horizontal and figure out, do I have an equation here that could help me solve? The second vertical, right? Will second vertical make it happen? Yeah, that's really the most common one that we'll use, okay? So my second vertical equation would say y final equals y initial plus VIT plus 1/2 a t squared. This is a really common, like for rolling projectiles, we're going to use that equation really often to solve for time. I got a time equal to 2.21 seconds. I don't know if that matches what you had. Yeah? Okay, so there's part of my answer. Next, it asks me how far from the base does it land? So what variable does that mean I'm solving for? X final, very good. X final, my final horizontal displacement. So that means I'm looking for like this distance right there in my diagram. Right? I want to know how far. So now I go to my horizontal equations. Sorry, did you have a question? Are you good? Okay, I think my second horizontal equation will work, right? X final equals X initial, which we always know is 0. Vxi times t. That gives me an X final of about 7.1 meters. And then the last question it asks is final vertical velocity. Okay, I'm sorry, I should have asked. Any questions about this X final? Okay, final vertical velocity would be VYF. VYF. I think I can use the first equation there, right? Our first vertical equation to help me solve for VYF. VYF equals VYI plus AT. And our vertical velocity comes out negative. Does that seem to match what we would expect? Yeah, because it's going downward. Yep, I plugged in the wrong number for time. Sorry. Okay. 9.8 times 2.21. So how about negative 21.7? Okay. Yep, thank you. Okay. So how do we feel about the problems? Do you feel like the hardest part is choosing the right variable to go with the number? Right? Really identifying that, okay, this is a velocity. Those are the questions I want you to ask yourself. So I want you to look first at what's the unit, right? Meters tells me it has to be a displacement. And so then you ask yourself, is it vertical or horizontal, right? Meters per second has to be velocity. So you ask yourself vertical or horizontal, right? Those are the types of things I want you to use to help you identify the different variables. Okay? A diver running 4.0 meters per second dives out horizontally from the edge of a cliff and 2.2 seconds later hits the water. How high was the cliff and how far from the base did he land? So I'll give you a head start and then I'll get this one up on the board here in just a minute.